So let's work through interpreting one example. Now, in this case, we have a velocity that is changing, and the velocity looks like a line. So what you'll see is that this is in fact just a constant acceleration, but we're not going to worry about that right now. What we want to do is figure out what our displacement is going to look like. And again, in this case, we can say what our initial velocity is. So at time equals 0, our initial velocity is 0. What we don't know, just from looking at this plot alone, is what your initial position was. Now again, in a problem, something's going to be described to you such that you should be able to read the problem and say, oh, I'm going to actually say that my initial position is equal to 0. But you need to make sure that you're making that very clear in your work, since that's not clear at all from this plot. That information is in no way contained in this plot. Now, there's two ways to approach this, and we're going to work through both ways to show that they're equivalent. So one is to think about the displacement as the area under the curve. So that's the area of the shaded triangle, as the text says here. And if you look at that, well, this is basically a triangle, literally. And I'm going to typically refer to this as integration by geometry. So I'm going to look and say, okay, I'm going to say my displacement, my change in position, is equal to 1/2 base times height. And my base is equal to 3 seconds, and my height is equal to 12 meters per second. Okay, so that gives me 36 meters divided by 2. So my displacement during this time is equal to 18 meters. So that's one way to do this. But now what if I wanted a functional form? So instead of just one value, I wanted displacement as a function of time. So let's just take some value here, t, and think about this triangle. So now my displacement as a function of time is still going to be 1/2 base times height, but my base is now equal to t. And what is the height equal to? So this is where we need to actually use this equation. And it's nice that they gave you an equation, but my hope would be that if you had a linear plot like this, that you could also just figure it out based on these 2 points. And so the height at that point is equal to 4t. Now this is one case where I'm not actually going to carry around my units per se, but technically it is, there's a meters per second happening here. So if I look at this, this is 4 divided by 2 t squared, which is equal to 2t squared. Another way of doing this is to just do the integral. So we can say that our displacement is equal to the integral of vx dt. Now I'm writing this as initially an indefinite, but let's make this a t initial to t. So if I want that, I probably want to switch this out and make this just d tau, so it's a little more clear. Now, in this case then, I'm going to plug in what my functional form is, and the fact that my initial time is equal to 0, and my functional form was equal to 4t. Now again, we don't want this to be t because I'm trying to come up with that in the end, so let's make that 4 tau d tau. Now when I integrate tau, I would get 1/2 tau squared. So doing out the integral, I'm going to have 2 tau squared evaluated at 0 and t, which is just going to equal 2t squared. So doing out the actual functional integral or doing out the geometry gives you the exact same answer. That's why it's okay to choose whichever one you think is easier. And depending on the situation, you might not be able to do a geometric interpretation, especially if this has a much more complicated functional form. So note now that if we had this plot of position that has that shape that we just described, that this is actually the same thing that we have here, except this was our velocity plot, so straight line, and our plot of position is then that parabola shape. And we had seen that as you take your derivative, you get your slope at each point, that would give you your instantaneous velocity. So be careful here in that sometimes students might look at a straight line for velocity and assume that you get a straight line for position, but that's obviously not true. What actually happens is you get a parabola for position. So please be careful about that, and what might help is remembering that integration relationship going from velocity to position. And that integration relationship is always true, whether velocity is a straight line or a very complicated functional form. So that's one way to try to remember that. So now let's look at another plot and try to interpret this. Now in this case you notice that this is again a straight line and it has a negative slope, so something that will be talked about in a later video, that this does in fact correspond to a constant acceleration. And note that this is x. So in this case we're talking about motion that is left or right, and rightward motion is positive x direction. So initially we have a positive velocity, and this is going to correspond to moving to the right. So think about this and be a little bit careful that even though this is decreasing, it's still a positive velocity. So this is still motion to the right, but it is slowing down. So it's slowing down up into this point here, and at this point velocity is 0. So this is where it is in fact stopped. And we would call this a turning point. So it is stopped and it is turning around. So what do we mean by a turning point? Well, down here, this is in fact moving to the left. And in this case, we aren't necessarily saying that it is physically to the left of where it started, simply that it's moving to the left. So here it's moving to the right, but slowing down, slowing down, slowing down, stopping. Now it's moving to the left. Now we could ask, at what point in time would we have a displacement of 0? That's in fact when your final position is equal to your initial position. So if I want to find where that is, that's equal to a displacement of 0. Now obviously, if you just take your initial starting point, that's true, but it might be true at a later time as well. Now what we would want in this case is for the integral of our velocity over time to equal 0. So where would we have area under the curve equal to 0? Well, notice that this entire part here, we have a positive area under the curve. So that entire time it is moving farther and farther and farther away. But then it stops and it starts coming back. So we would call this, and remember this area here actually is then negative area under the curve, right? So this is negative in our integral. So if you look, this lower piece here and this upper piece here are equal, but this one is positive and this one is negative. So at this time here, so the position of 4 seconds is in fact equal to our initial position because our total displacement is 0. So this is what I mean when I talk about interpreting a velocity plot, that even though you haven't been given a plot of position or of displacement, you're able to use the information in the velocity plot to infer what's happening with position. So this is where we need to really be able to work with representations, and you can get a lot out of it without ever doing a calculation. So please don't undervalue these visual representations, whether it's a motion diagram, which you could certainly make for this situation as well, or whether it is for a plot like this. So after 4 seconds, it's gotten back to its original point, but it's still moving to the left. So it's now left of its initial position, and it's speeding up, going further to the left. So that's what's happening in this situation. So to give a really brief summary, the main thing to remember is that you need to integrate the instantaneous velocity to get displacement. That's always true. And if your velocity is a simple enough shape, you can do that via geometry. Otherwise, you might need to do a proper integral. But on a plot, that means that that's the area under the curve. Being careful to make sure that you see the difference between a positive area under the curve and the negative area under the curve. The other thing that I want to stress is that whenever you're working with velocity, you don't know initial position, so you either need to define it in your coordinate system, read the problem carefully to see if an initial position has been given to you, or just work with displacement, which is frequently something that's very reasonable to do.